It's about frequency transfer. IPPP is precise point positioning with integer ambiguities, and this is about the use of IGS products proposed by the Analysis Center, GRG, with my co-authors involved here. So for those of you who don't know much about what we are talking about, frequency transfer and clocks to be compared, this is a short sketch showing the types of clocks and frequency transfer uncertainty that we aim at for standard commercial clocks, 10-14, 10-15, for the best cesium fountains, 10-16, and for the coming atomic cold atom clocks or trapped ion, 10-17 and 10-15. And the classical methods of GPS, GNSS, or two-way time transfer easily compare those clocks and come somewhere to compare the fountains. But you only have the fibers to cover the whole range, and this is not easily done, of course. Next year we should have the ACES mission flying aboard the ISS, and its special microwave link, which should go somewhere in the 10-17 and maybe a bit more. But anyway, it's not flying now, and it will be only a short mission. So there is really a need for technique, and this PPP with integer ambiguity is trying to fill the gap somewhere here. So just a reminder and some comparison, recent comparison of IPPP with other links. So you know that due to the ambiguous nature of the phase, everything is ambiguous when you compute time transfer with phase clocks. And you do this on different batches, and you have to ensure the continuity from batch to batch. And this is a source of uncertainty in the classical PPP. And taking into account the integer nature of ambiguities allows, in principle, to rigorously solve the problem of the boundary discontinuities. And but to do this, you need to have products which are derived consistently with taking into account the integer nature of ambiguity. So this is these products are generated by the GRG Analysis Center of the IGS, the products that are used in the IPPP application that I will show. And then with these products available, the user can take the products and do PPP with integer ambiguities. For example, with the GINS software developed by the CNES, but you can develop your own software if you wish. So this process is, as I will describe, is a two-step process. So first, there is zero difference. So of course, you have to determine two ambiguities at the two frequencies, because we are dealing with dual frequency measurements. So in this process, we first determine the difference between the two ambiguities, N2 minus N1, and then N1. And well, I will not get into details, otherwise it will take more than the 15 minutes of this talk. So the first step is based in the based on the Melbourne-Wegener linear combination, and based on the transmitter satellite bias, wide-lane bias, which is derived by GRG, and you determine the wide-lane bias of the receiver and the difference between the two ambiguities. And in the second step, which is done by batches, you just write the iono-free phase solution, and you can see that you have to determine a set of integer ambiguities set because there is one for each pass, and the station clocks. Difference between provided satellite clocks and the receiver clock that you want to determine. And you see that there is complete correlation between clocks and ambiguity. Any error in the ambiguity will go into the clock, and there is a global degeneracy. You have one ambiguity to determine when you want to go from one day batch to the next day batch. You have an unknown integer ambiguity, which is at the level of 10 centimeters, or if we, because we are in time, 350 picoseconds. So the point is to be able to determine this link from day to day or from batch to this level. And this is done when you have stable clocks like hydrogen maser. You should be able to just extrapolate forward or backward to determine this integer number. If you don't have hydrogen maser, then you are in trouble because instability of the clock can easily reach the level where you get confused. And then you should use some bridging technique. I mean, another independent, preferably frequency technique that allows you to choose which integer number you should choose to link the day to the next day. So the question is whether this can be successful. And by comparison to other links, I will show you that this is successful. All this technique was more or less developed 3 years ago and first published in 2015. And in this presentation, in this publication, and also in this presentation, we are still have one main source of comparison, which is one fiber link, which is available between two laboratories in Poland, and which has been reported to the BIPM for many years now. So this fiber link is easily providing a 10-17 accuracy at 1 day at least. So for us, it's ground truth. And when you compare on this link the classical PPP solution, which is here in red, and you have total scale of about 1 nanosecond here. And the IPPP, which is in blue, you can see that the stability of IPPP is much better, and this turns to frequency instability, which is in the 10-16 level at about 3-4 days averaging. This has been repeated month after month, and of course the problem with this kind of phase comparison is that you need a phase continuity, or at least a good, not too big gaps in your data. And it's very difficult to have this operationally for months. So actually, since we have this fiber link available, found 104-day interval where everything was continuous. And on this 104-day interval, the IPPP comparison to the fiber link is in blue here. So varies by a few hundred picoseconds over the 100 days. While of course, when you compute a continuous classical PPP solution, then you have just random variation. I mean, you could do something better by steering with the code more often. Well, we can discuss this, but anyway, the point is that the IPPP solution goes down to the low 10-17 level at above 10 days, let's say. And the frequency difference is not significantly shifted. It's in the 210-15 level. We have other techniques which are more in the study phase for two-way time transfer, for example, to which we can compare the IPPP, and I will briefly show a couple of them. One is using new analysis techniques with, instead of hardware receiver, doing software receiver. And again, we can see this provides IPPP better consistency with the two-way SDR result than the classical PPP. Of course, here we don't know exactly who is the limiting technique, if it's IPPP or if it's a two-way. At short term, it's mostly two-way because it's a code technique. But two-way can also use a carrier phase, and in that case, the carrier phase from two-way is much more accurate at short term because it's higher frequency, it's free from tropospheric problems and free from multipath because it's a directive technique. So the two-way carrier phase at short term is much better than what we can do with GPS. And we compared the two-way carrier phase and IPPP over 1,000 kilometer baseline between Korea and Japan. And so again, the IPPP is better compared to two-way carrier phase than the classical PPP. But at this point, we know that the short term in the two-way carrier phase is better. And the comparison, which is in light blue, here goes down to the 10⁻16 level in 2 days for this case. So it's a quite good result. So to conclude, to get to the 1/10⁻16 level and below, IPPP is a very interesting option because it's available readily anywhere. You just need to have some geodetic receiver with time reference, and of course you need continuous measurements. But I would say you can allow gaps in your data if they are not too long, and it provides something in the 10⁻17 above 10 days, with some room for improvement. So for the future, there are more questions than answer, but an interesting topic to cover. Thank you very much.